Number 9, be able to define average bond enthalpy. So a couple things is it's energy to break bonds, and it's to break 1 mole of bonds, and it has to be in a gaseous compound. So that's the second point you need to make. So energy to break 1 mole of bonds in a gaseous compound averaged for the same bond in similar compounds. So it's breaking 1 mole of bonds, they have to be gases, and it has to be averaged. Know what factors increase bond enthalpy? This is one you may not have picked up on in the reading, but something you should realize is if it's a single, double, or triple bond, so multiple bonds are stronger than single covalent bonds, so that's going to increase enthalpy. So bond length. Shorter bonds are harder to break. Remember, think about it like being a stick. Other things that'll affect it is the size of the atoms bonding. Smaller atoms tend to bond tighter because the nucleus is closer to those shared covalent bonds. And then another thing that'll affect it is the polarity of the bond or the molecules. Okay, more polar will tend to hang on more tightly. So it's the same things that tend to increase the strength of a covalent bond because that's what we're breaking here. So multiple bonds, size of atoms, polarity of the bonds, those are kind of the most common ones. Know what assumptions are commonly made when finding enthalpy of solvation using a calorimeter, and know how these assumptions affect your results. So the big assumptions are density of solution is equal to the density of water. But in reality, solution will be more dense. So how does this affect your results? So mass is underestimated and decreases the final delta H that you find. Second solution is that the heat capacity, C value of solution, is equal to water's heat capacity. And we don't know if the solution's actual C value is higher or lower. So we're not aware of the effect. Another big one is that all heat from solution is retained. In other words, no heat loss, either to the calorimeter or the surroundings. And again, which of course there's heat loss. So our change in enthalpy is lower than the actual. And then the last one is that the reaction, or in this case, the solvation, dissolving, is complete. And you could even say uniform. So not only does all of it dissolve, but the heat is spread equally throughout so that your thermometer doesn't have a chance of being at a hot spot or a cool spot, which is a reason for using the magnetic stirrers. And that really shouldn't be too hard to accomplish, to have a complete solvation occur, a complete dissolving occur, if you wait long enough to reach a maximum temperature. But if it weren't, the temperature change will be lower, and then your enthalpy change will also be lower. And to be more precise up here, so the change in temperature and therefore enthalpy is lower than the actual enthalpy change. So those are kind of the big ones as far as what does or doesn't. Sorry, I got a mess here with all my formatting, but those are the big things that we assume when we use calorimeters to do salvation.